Welcome to the Deep Dive, where we take the hardest concepts in science and philosophy and really try to drill down to their fundamental truths.
Or the really fascinating questions they leave us with.
Exactly. Today, we're jumping into, well, what might be the most cutting-edge realm of theoretical physics.
It's this idea that gravity, geometry, maybe even matter itself are not fundamental things.
Right. They're not forces or objects, but just emergent properties of thermodynamics and information flow.
It's a huge conceptual leap, and we're looking at sources that detail two major efforts to really formalize this idea of entropic gravity.
Oh, yeah.
So on one side, we've got Ginestra Bianconi's work. You often see it summarized as gravity from entropy. It's highly elegant, and it's built on very established informational principles.
And on the other side of that, we're comparing it to a much more sweeping, unified approach. It's known as the theory of entropicity, or ToE, formulated by Obidi.
And both rely heavily on the concept of entropy.
But they disagree, and pretty dramatically, on what reality actually is.
So our mission today, really, is to get to the bottom of that disagreement. We need to unpack the philosophical and the mathematical divergence between these two frameworks.
And specifically, we want to understand the exact mechanism by which Bianconi's theory is shown to be a kind of restricted limit.
A special case, a near equilibrium version, inside the much broader structure of the theory of entropicity.
So let's jump right into the core of the problem, because the fundamental difference is ontological. It's about what is. If you ask these theories, what is spacetime? They give you these radically different answers. Our sources are clear that Bianconi's theory is built on two separate things, while ToE insists there's only one.
That's the crux of it. Bianconi's formulation uses what we call a dual ontology.
Dual ontology.
To derive the dynamics of gravity, her theory has to distinguish between two different geometric structures. There's the background space-time metric, which is Jimunu.
Okay, the standard one.
And then a separate matter-induced metric, Minunu.
So we have two metrics, two spacetimes, basically existing in parallel.
Exactly. And gravity is the force that emerges from the informational divergence, the statistical distance, calculated between these two separate geometric structures.
It's like comparing two different maps of the same territory.
That's a great analogy. And the differences between the maps, that's what generates the dynamics.
So how does the theory of entropicity counter that dual structure?
ToE is much more radical. It commits to what it calls a unitary entropic ontology.
Just one thing.
Just one thing. It posits a single, all-encompassing fundamental field, and that's the entropic field, S of x. In this view, there's no separate background space-time, no separate matter geometry.
So all of it. Geometry, matter, even the flow of time.
All of it. They're just emergent projections of the single entropic substrate.
Okay, let's unpack this. If the universe is built on a single entropic field and not a comparison between two metrics, then what is gravity? If it's not the informational mismatch, what's the process that warps spacetime?
In ToE, geometry is the shape of entropy flow.
The shape of the flow itself.
Right. Curvature and gravity are the direct geometric shadows cast by entropy gradients, by how that field S of x changes across space.
So the gravitational field equations, the Jimunu that define curvature.
They are directly linked to the second derivatives of the entropy field. We can kind of sketch that relationship as Jimunu. Well, it comes from the double gradient of S.
So gravity is just what we see when energy and information are trying to reach maximal entropy.
It's the visible manifestation of that cosmic process.
Okay, so that really draws a clear line in the sand then. Bianconi sees gravity as relational, the information and the difference between two things. And ToE sees gravity as intrinsic, the inherent curvature built into the flow of the one fundamental thing.
Let's dig a bit deeper into Bianconi's commitment to that duality. The core mathematical engine is the informational action. It's IB equals KB times dril of G parallel to M.
And that term, dril, that's the quantum relative entropy.
Exactly. And it's basically measuring how distinguishable the two metrics, G and M, really are.
And this is crucial, right? Because in classical information theory, dril, which is also called Kullback-Leibler divergence, it requires two distinct probability distributions to compare.
You can't define the divergence of a single state. It's not possible.
So the math itself dictates the philosophy.
It really does. Because the machinery of relative entropy needs a reference state, that's Jimunu, and a perturbed state, Munu. Bianconi's theory is just forced to include two distinct informational spacetimes existing at the same time.
Which leads to what our sources call Bianconi's paradox.
Right.
If the background metric Gi mu nu is an informational baseline that matter doesn't physically deform,
Yeah.
and nu mu nu is this parallel informational geometry,
Right.
then the interaction isn't physical bending like in Newton or Einstein.
No, it's not. It's pure informational comparison.
And that comes with a heavy ontological cost.
It does, because if the physical interaction is just calculating d-rel, then you have to ask what's actually real.
Is it the geometric substance? Is it the matter?
Or is reality the relation itself, the informational divergence? Bianconi's framework really struggles with that dualism.
Okay, so if Bianconi's theory pays that ontological price, how does ToE manage to get the two metrics it needs for the comparison while still saying there's only one fundamental field, S of x?
It's clever. ToE internalizes the comparison. The two metrics Bianconi needs aren't separate realities.
They're just different views of the same thing.
Exactly. There are two different mathematical projections of the same unitary entropic field, S of x, just viewed through different lenses.
Help us understand those lenses. What are these projections conceptually?
Okay, imagine the entropic field S of x is like a vast vibrating membrane. When we look at the standard large-scale geometry that obeys general relativity, that's Gi mu nu.
Right.
In ToE, Gi mu nu is recovered as what's called the Levi-Civita slice of the Fischer-Rao metric, which is the natural geometry of statistical space.
Induced by the entropy gradients. Let's pause there because that sounds really important. The Levi-Civita connection is essential for general relativity. It's what guarantees local conservation laws. So by showing Gi mu nu comes from the Fischer-Rao metric, ToE is immediately linking the geometry of statistics to the geometry of local physics.
Precisely. It's an incredibly powerful unification. And then the second metric, mu nu, is just the deformation of that same underlying entropy geometry.
When matter is present.
When matter excitations, these localized pockets of information are present. It's the difference between the geometry of the relaxed membrane and the geometry of the membrane when you put a weight on it.
So the geometry is one thing, but the comparison is between its equilibrium state and its excited state.
Yes, and this is why ToE recovers Bianconi's relative entropy functional so cleanly.
Ah.
ToE shows that the informational comparison that d-rel needs is internal to the field S of x itself. It's just measuring the deviation of the actual entropy configuration, S, from the system's equilibrium configuration, SEQ.
And mathematically, you see that because d-rel is recovered as a quadratic approximation of this deviation. It's something like d-rel is approximately 1 over 2 KIB times the integral of S minus SEQ squared.
And the significance of that quadratic approximation is that it shows Bianconi's entire framework only describes what happens when the universe is operating close to equilibrium.
When the entropy differences are small.
Exactly, when the geometry is only slightly perturbed.
So the implication then is that ToE fully embeds these foundational structures. General relativity's local physics and information geometry's statistical measures, all within the universal dynamics of this single entropic field.
And that's why Bianconi's work, for all its elegance, is classified as a special case.
The restricted regime of ToE.
Yes. It's really only valid in that near equilibrium weak gradient limit where the informational geometry and the dynamics are time-symmetric.
Time-symmetric dynamics, meaning the process looks the same forwards and backwards in time. But real thermodynamics and life itself are fundamentally time asymmetric. They're driven by irreversible entropy flux. So if Bianconi's theory is stuck in that time-symmetric limit, what happens when ToE opens the door to irreversible dynamics?
Well, that's where the true generalization happens. ToE naturally includes irreversible dynamics, where SR is not zero, and that allows it to describe phenomena far from equilibrium.
Like the emergence of complex structures.
But critically, the continuous expansion of the universe.
And this is where it gets really interesting. This brings us to the cosmological implications. Let's talk about the cosmological constant, lambda, which represents the dark energy driving accelerated expansion. How do these two entropy-based theories explain it?
Well, Bianconi's theory does generate a small positive lambda, but it needs to introduce an auxiliary constraint field, a G field, to enforce the entropy flux conditions. Lambda emerges as a consequence of those constraints.
So it's emergent, but maybe a little shoehorned in.
You could say that. ToE, on the other hand, derives lambda rigorously and fundamentally from the entropic field itself. It defines the entropic cosmological constant, lambda, as the coarse-grained variance of entropy gradients across cosmological domains.
Wait. So lambda int is equal to the average of the gradient of squared.
That's the one. Lambda equals the average of del S squared.
So the cosmological constant, what we perceive as dark energy, is literally the measure of how much the entropy flow varies across vast regions of space.
Yes. The cosmological constant is the background roughness or texture of the entropic field itself, and this provides a natural physical explanation for dark energy without needing any ad hoc fields or fine-tuning.
It's a self-consistent outcome of the universe trying to maximize entropy.
Exactly.
That structural difference is incredible.
Mm.
Okay, let's pivot to the math of ToE, specifically its field equations. Our sources point out that ToE's equations are fundamentally recursive, which is not like the closed-form solutions we look for in general relativity.
This is arguably the most radical mathematical shift. Einstein's equations, you can plug in a matter distribution and solve for the geometry directly.
Right.
But ToE's fundamental equation, which is box S minus V prime of S plus J of S equals 0, is recursive. That source term, J, which defines the interaction, it's a functional of the solution S itself.
Meaning the source depends on the state of the field, which then defines the source.
Yeah.
It's a continuous feedback loop.
It is. You can't solve for S in one go. You have to compute iteratively. S at step n plus 1 depends on the calculation you did at step n.
And that recursive structure isn't just a mathematical quirk.
Not at all. It provides a direct analog of adaptive intelligence or learning algorithms.
So we have to reconsider what we even mean by a universal law. If the physics requires iterative computation, the universe isn't just following static rules, it's constantly updating itself in response to its own previous informational state.
It really shifts the ontology from a clockwork universe to an active, self-correcting system.
Which has huge implications for observation.
Absolutely. If the universe is adaptive, we might need to look for non-static, emergent behaviors that we just wouldn't predict using traditional closed-form gravitational models.
So, to synthesize this entire deep dive, we move from Bianconi's sophisticated but constrained informational duality, where gravity is a mismatch,
between two separate geometries,
to the theory of Entropicity's complete entropic monism, where gravity is just the manifestation of the entropy gradient of a single universal field.
And we established that Bianconi's framework is an essential but constrained piece of that puzzle. It's the low-frequency, time-symmetric slice of the universal theory of entropicity.
Valid only when the system is near its informational equilibrium.
Exactly.
So what does this all mean for the history of physics?
I think it frames the historical progression of gravitational theory, not just as steps in precision, but as deepening ontological commitments.
Okay.
You go from Newton's instantaneous force to Einstein's geometric curvature to Bianconi's informational mismatch, and finally to ToE's realization that the underlying mechanism is entropic recursion.
The universal language is information flow and self-correction.
That's the picture it paints.
And that leaves us with a really provocative final thought for you to chew on. If the foundational field equations of the universe require iterative computation and inherently mimic adaptive intelligence, does this suggest that existence isn't just a process of physical interaction, but maybe it's one of universal self-correcting computation, all driven by entropy? And if the universe is constantly learning, what experimental signature should we be looking for that would confirm we are living inside a vast, recursive informational field?